Dzień dobry. Tam jeszcze musisz kliknąć gotyc. Moje palce są czarodziejskie. Nie, czekaj. Dobrze.
Okay, hello again. Welcome to Warsaw University Astronomical Observatory Tuesday seminar series. Sorry for a slight delay. We're struggling with technicalities. Every week is something new. But I hope we managed. I hope we are live on YouTube and we're recording this as well. And today we have a guest from Poznan University, Adam Mickiewicz. University, Agnieszka Kryszczynska, who's going to tell us about small bodies near and far.
Thank you for invitation. And I will tell you a story about small bodies of the solar system, which are near and far, really, because there is a lot of them in our solar system. So at these photos, you have the old telescope, which is located in our park. But the next telescopes are located. This one is automatic robotic telescope in Arizona. And this set of telescopes are located in Halin in a dark sky area. But these are devoted mainly to satellite and space debris observations. At the beginning, I will start with the short presentation of my observatory. So what do we do? We work on the physical parameters of small bodies of the solar system. So from the observations, photometric, spectroscopic, and others, we can model their physical properties. We can make surface modeling of near-Earth objects, far objects. We can do also taxonomy. We work on asteroid families, their orbital parameters, and also on non-gravitational effects, which are quite interesting. The next topics which are studied at our observatory are dynamics of artificial satellites and space debris, dynamics and origin of comets, and also meteorite streams, and astrophysical part connected with stellar astrophysics and galactic astronomy. But historically, these small bodies are, we are really deeply involved in that project. With this project, we are involved in several, mainly international projects. Small bodies near and far. It was a title of Horizon 2020 grant, which we took in part in this project with Thomas Miller, from Max Planck Institute for Extraterrestrial Physics, and from our side, Ania Marciniak was the PI of this project. We also took part in a long period project observations of asteroids on VLT sphere instrument. And we are also involved in observations of small bodies of small near-Earth asteroids at SALT telescope. And also we provide some projects from National Science Center. And also the last project is the Europlanet 2024 research infrastructure, which is Horizon 2020 project. Oh, sorry. I was too fast. We work also with the European Space Agency on services which help observations of small bodies of the solar system. And this project were, some are completed, some are still ongoing. They are all connected with near-Earth objects. And the last one is connected exactly with observations of the near-Earth object on the southern hemisphere. You know that the southern hemisphere is not so efficient in observations of small bodies of the solar system because of the lack of telescopes, in fact. And we are making tests of these kind of observations. Some of these services will be implemented on European Space Agency website, and some of them are implemented at our website. So what are the small solar system bodies? Oh, it doesn't work well. I cannot skip over one. Nowadays, we know more than 1,100,000 bodies in our solar system. All of these bodies have well-defined orbits, and you see here inner solar system. In red, we see near-Earth objects. In green, there are main belt asteroids. In blue, Jupiter Trojans. And here you see the outer solar system, where orbit of Jupiter is the most inner here. And the dots here are so-called Centaurs and also Kuiper Belt objects. We study, in fact, all of these kinds. Here is a zoom of these two animations. Why do we study near-Earth objects? Sorry, small solar system objects. It's the goal of this study is to solve the mystery of our solar system formation. And in fact, small bodies witness the history of the solar system from its beginning, from the accretion disk around the sun. And during the more than 4 and 6 billion years of the history of our solar system, small bodies were influenced especially by big planets, by giant planets. As the giant planets move during the history of the solar system, and at the beginning they move, especially Jupiter and Saturn, they move in to the inner parts of the solar system. Then after trapping in resonance, they move outward in the solar system. During this travel, they influence all small solar system bodies which were formed from the beginning, even till the last part of a known history. Sorry. Okay, thank you. Sorry, I have to be careful. The models of history of the solar system are divided into two parts. The first one is the Grand Track model, which is connected with journey of the Jupiter inside the solar system, and then the Grand Track, a big, in fact, jump or changes of direction of the moon of Jupiter. You can see Jupiter was very close in the solar system, close, in fact, to the orbit of the place where the Mars was formed, and that's why the Mars is so small. The rest of the journey of big planets in the solar system is connected with mass removal and the mixing of objects in the solar system from the outer parts, and some were injected in the vicinity of the Earth and the Sun, and some were ejected to the outer parts of the solar system. We studied these bodies as a single object. We study families, and we study small bodies as the whole population. The most interesting objects were differentiated planetesimals. the very primordial, very old objects which still survived in our solar system. What techniques we use to get the physical parameters? The easiest are, of course, light curves. So we observe light curves to determine, here you see an example of light curves, so changes of brightness in rotation. Light curves allow us to determine rotational periods and also phase curves and models. Then we can use also fast photometry to observe the occultations of stars by asteroids, also for modeling and for size determination. We can do low resolution spectroscopy. Here there is an example of low resolution spectra of asteroid, visible part and infrared part. This reflectance spectra are connected with the parameters of the surface of those objects. We can use also adaptive optics, but of course it is very hard to get time on VLT to obtain such good, in fact, pictures of small solar system bodies. Very efficient is also a technique called occultations, and it is simple, a very simple method, because we see on the ground, on the Earth, a shadow of the asteroid, and from the shadow we can detect the size of the object, as well as, for example, satellites, and maybe something more interesting also. Here is a comparison of adaptive optics images in the first row. The modeling of the asteroid developed in Helsinki University. It's all data asteroid modeling technique. But at our observatory, we developed a SAGE method. SAGE means shaping asteroid with genetic algorithms. And as you can see, this technique based only on photometric light curves is very efficient in asteroid modeling. Of course, we do not need to see all of the asteroids by VLT sphere instrument, but we can compare the results, our results. Sorry, we can compare our results with, for example, occultations and shapes obtained from occultations. Of course, this method, it was many years spent on developing of this method, and shaping started from two, in case of the binary object, the shaping of asteroids started from two ellipsoids, triaxial ellipsoids. And this light curves presented here for sure reminds you the light curves of eclipsing binary stars. We observe the same eclipses in case of binary asteroids. And from such light curves, such observations, we can determine model of such object. As I told you, it was the beginning, but now it's of course much further. So we can model these objects as two non-convex shapes. These models were based only on photometry, but of course we can add adaptive optics or observations to modeling, and also a next step, which is the work in progress, will be application of radar images. Unfortunately, we will not probably have more radar data because Arecibo is down. So we will have to use the archive of Arecibo. These models are calculated on our computer cluster at the observatory, so it is a really good place to make such models. Models which we derived are available by internet, by the service which is called Interactive Service for Asteroid Models. And several hundreds of models are implemented to this service, and everybody can predict the future behavior of the light curve of any object which is in the database, or we can go to the past and check what kind of observations could be done before. Shapes and sizes of asteroids can be verified by occultations. So this is the same figure I presented you some time ago, but here you can see the model of one object which is called Sylvia, and it is projected on the plane of observed chords of the occultations. The model fits almost perfectly to the shape derived from just light curves. So this technique helps us to verify the models we predict, in fact, and also help us to scale the model, because this distance, in fact, between two observations, beginning and the end of the occultation, gives us direct size of the object. And if we have direct size, we can then, having, for example, mass, we can determine density, which is very, very important. From occultation events, if we have good cameras, very fast cameras, we can observe not only a main occultation, but sometimes we observe additional events. And this case here is a case of dwarf planet Haumea, which is at the distance of more than 30 astronomical units from the Earth, also from the Sun. It is in Kuiper Belt, and here on this plot you see the light curve of occultation, but the light curve is has some additional events, and at the beginning it was not known what happened. But if such observations were observed by several observatories, the interpretation of this occultation was like this. So from the main occultation, we can detect the size and shape of this dwarf planet. It appeared to be larger than predicted before this occultation event. We could also determine the albedo of this object, which also was 50%. It's really high albedo for so distant object. We could also determine the limit for its density, and also observations of this occultation showed that around this object we see a ring. It is the first ring discovered around the dwarf planet, similar to the rings which are observed around Jupiter, Saturn, Uranus, and Neptune. And one also Centaur has, which is called Chariklo, also has a ring, dust ring, of course, it is dust ring, which lies in the equatorial plane of this planet. It also lies in the same plane as the one of the satellite of Haumea. This ring is inside the Roche limit of this body, so it is not a problem with interpretation. What is it? And the size of this ring is about 70. The diameter of the ring is about 70 kilometers. So it is really important information. Why Haumea could have a ring? Because it is a very big object which rotates very fast, and probably the dust is ejected from the surface of Haumea and forms this kind of ring. From distant object, we observed also very strange case. It is a case of a Heclus. It was discovered as a Centaur object and at the beginning of this century. It was close to aphelion at that moment, but some years later, the big outburst of this body was observed. Outburst, it means that from 21 magnitude in one night, it changes brightness to 14. So seven magnitudes became 7 magnitudes brighter. What was strange, this activity disappeared after some time, and here it was not observed because it was very faint. And then it was a second outburst, and the third and fourth outburst just after the perihelion passage. This object is really very surprising, as it has cometary activity on the orbit similar to Centaurs, which are not active. And between outbursts, we obtained several light curves, which allowed us to make its model also. Here on these plots, you see the data of the outburst from 2016, observed at VLT on force 2. It is visible that the activity is fading, in fact, during time. In 2019, at the end of the 2019, and this apparition, this body has no cometary activity, and using light curves, we were able. It's not all of them, of course. Some part of our light curves. We were able to obtain model for this body. Here is a map of the post solution where red places show the best solution, obtained best solution. Now moving to asteroid populations, we can study populations working on asteroid phase curves, and phase curves are very important in case of determination of physical parameters, of surface parameters of these objects. As described by Antti Pentila 5 years ago, different type of objects have different slopes of the phase curve. So here we have phase angle and reduced magnitude, and also different opposition effect. Opposition effect, it's an effect of brightening of the object when it is its phase angle is less than 5 degrees. Such phase curves are much easier to obtain than the spectra of asteroids. That's why we like to use them. But the problem is that phase curve is problematic in case of big amplitude of asteroid light curve. So how to solve the problem of determination of its type from phase curve if the object has a high amplitude light curve? These of course are simulated. Now here are simulated data. So we have to correct these changes of brightness caused by rotation and use only average brightness or maximum brightness. We have decided to use maximum brightness, and then the case is much easier. We can obtain very precise phase curve. These phase curves are obtained for our favorite objects, V-type objects, which are very primordial type, which is very primordial type. And you can see that even if we add 19 objects on one graph, the slope of the phase curve is the same for all objects. In fact, it's the same for all objects. It means that with this technique, we can determine the type of the object. This was the first survey of phase curve, precise phase curve for V-type asteroids. So it took a lot of time for us to obtain this data. Phase curves we can also determine using Gaia, data from Gaia. Unfortunately, in the Gaia DR2, we had only several thousand asteroids. We expect more than 120,000, maybe even more. But phase curve obtained only from Gaia data is not enough, in fact. Blue points are points from Gaia. You can see here, blue points are points from Gaia, which are very far from the adjusted curve. We can obtain only the linear part of the phase curve because Gaia observes at large phase angles. To reduce the effect of the amplitude of the light curve, we can connect Gaia data, these points in black are Gaia data, and correct this data for the amplitude of the light curve. And here on the top of this figure, you see corrected phase curve for one of our target. So improvement of Gaia data by the amplitude of asteroid light curve allows us to get the correct slope of the phase curve. You can see sometimes it's even worse case that Gaia data show completely opposite effect than it is expected. So correcting these points by the amplitude, it is even not large, but here it is also not large scale. Improve the phase curve of such object. In the future, we plan to combine Gaia data with other sky surveys, which are not dedicated to asteroids, but we can use the data from the surveys and combine them with Gaia. Phase curves and spectra also can help in asteroids physical parameters determination, and historically spectra were the first. But in fact, before spectra, the taxonomy was done only on observations in 3 colors, then in 8 colors plus albedo. Then from SDSS, we had better distribution of points according to the wavelengths. But in fact, all our current knowledge on asteroids types is connected with near visual and near-Earth spectra, near-infrared spectra, or combined visual and near-infrared spectra. This is not efficient method to obtain asteroid photometer parameters because we need a big telescope, at least the IRTF telescope in Hawaii, to obtain such spectrum. On the spectrum, based on the spectrum, taxonomy of asteroids was developed in some years, no, maybe not some, about 20 years ago. But now we know that the complexes and type of asteroids are not enough to determine the physical parameters. These effects, which are observed in changes of the spectrum, could be caused only by space weathering. Collisions between asteroids could cause changes of the spectrum, and numeric simulations in the laboratories show that when 2 objects collide, their surface parameters can change completely. That's why we decided to work on new asteroid taxonomy. So not based only on spectrum, but we want to combine data from different techniques to get new asteroid taxonomy. And we plan, in fact, we already started to use machine learning algorithms to determine asteroid physical parameters. So it is a work in progress, and we work on several kinds of machine learning techniques, algorithms. And for now, we know that the best approach is using neural networks. In fact, it is multi-layer perceptron method, when we use several layers containing 32 or 64 neurons. This new approach combines in our new taxonomy method spectra, color indices, polarimetry, also albedos, phase curves, and meteorite spectra. So we want to collect all possible informations about asteroids to get new taxonomy. This is the work in progress, but I hope we will manage to do it. And now appendix connected with Szymon lecture from 2 weeks ago. Yeah, you had a lecture about the sources of meteorites. You talked. In fact, this is the famous graph made by Vincenzo Zappala, describing where near-Earth objects comes from. The resonances, main motion resonances, which exist in our solar system, are for sure sources of objects which comes to the vicinity of the Earth. But how to jump to the resonance? If we assume that the sources of the bodies in the resonance are collisions between two bodies, we should assume that the collision appeared very close to the resonance. Collisions itself cannot be a source of the body in the vicinity of Earth. But how to jump to the resonance? We can check if maybe there is another effect observed in the solar system which moves asteroids on their orbits and help to jump to the resonance. And this effect is called Yarkovsky effect. And Yarkovsky effect was described by, in fact, Jan Yarkovsky more than 100 years ago. However, his paper did not survive till now. But maybe I will show the next screen. Yarkovsky effect is an effect which changes the asteroid semi-major axis. It is caused by rotation of the object, which receives the sunlight from one side and re-emits the sunlight in infrared after some time, after rotation of a particular angle. And because of the difference in direction of the sunlight, the emission, light emission by the surface of the object, a very tiny effect appears on the orbital parameters of this object. And if the object rotates in the prograde direction, so in the same direction like the Earth, the Yarkovsky drift expands the orbit, and if it is the opposite rotation, Yarkovsky drift shrink the orbit. if the Yarkovsky is the theoretical source of the object in resonances, the number of retrograde and prograde rotators among the asteroids in the near-Earth object in the Earth vicinity should be 2. If the collisions are the source of the object in resonances, the distribution of asteroid spin vectors should be random. And in fact, the result is like this, that we have exactly 2 in the ratio between the prograde and retrograde rotators. So the Yarkovsky is for sure the main power, in fact, which produce objects in resonant orbits. Why it is like this? Because here on this, this is the semi-major axis of the body and inclination of the orbit. And you see the main resonances in the asteroid belt, which are connected to the Jupiter or Saturn. But here in the inner part of the main belt, we see a secular resonance with Saturn. And this secular resonance with Saturn is especially effective in delivering asteroids in the vicinity of Earth. But to this resonance, only retrograde object could jump. Yeah, so they can move only from when they are retrograde, so when the orbit is shrinking. Yarkovsky, it is not only the effect which influenced the orbit. The Yarkovsky also influenced the spin vector of asteroids. In fact, it is called YORP, Yarkovsky-O'Keefe-Radzewski-Paddock effect, and it can spin up, sometimes spin down, but mainly spin up asteroid rotation. What we see on this graph is log D log P log D log P, no jakieś zależność, zapomniałam. Relation. Here you see diameter of the object on logarithmic scale, and here on the vertical axis the period of rotation. Asteroids, larger than 150 meters, rotate with periods longer than 2.2 hours. These bodies here are probably, or most probably, rubble piles. So they are gravitational aggregates of many objects. But here, after this line 150 meters, we observe probably monolithic bodies. So simply stones. And these stones are smaller than 150 meters. Such stones we can observe also when they come very close to the Earth. And this year we observed the object, which is, this is its number, DW1, and the size of this object was about 30 meters. It was not the smallest we observed. And this is this path of the sky of this object in equatorial coordinates. The object was observed only during 5 days, but in these 5 days, it travels 170 degrees on the sky. So it was very, very fast. Exposure times we used for observations were 1 to 10 seconds. And this object, here you see composite light curve of this object. This object rotated, rotated with the period of 49 seconds. So this is such objects, these monolithic bodies rotate so fast because they are simply stones. What happens after, even if this period of rotation is shorter, we don't know. Maybe they disappear, they disrupt but probably such objects exist only because they are monolithic bodies. The predicted changes of rotation of the object we observed is like this. So it will shorten the period of rotation, and probably in that part here of this graph, it will disappear because we cannot observe objects rotating faster than particular period, because these curves, maybe not curves, but these straight lines are calculated for different tensile strengths of the body, which rotates very fast, and these bodies, in fact, could be formed from stone or from ice. Yes, so the strength, the tensile strength of such object is different. Maybe they disappear here when they obtain a very, very fast rotation of the order of several seconds. Or maybe we cannot observe, we cannot detect this. It is also possible, but probably not. Because it was not the smallest object. Some years ago, we observed 3-meter object, which was, in fact, the object was smaller than the telescope we used, because it was observed on salt. So telescope was larger than the object. Here is the model of this object, how we can interpret the light curves. And this is what I wanted to say, but I wanted to advertise a lecture which will be in a seminar in 2 or 3 weeks by Edyta Podlewska-Gaca, and she will talk about the program of observations of asteroids on ISO VLT. And this large program, long period program, allows us to observe more than 40 objects, and we got 150 hours on VLT. So this is the work which Edyta will present. The results are really interesting, and even the program lasts only 3 years. In fact, we were able to publish 14 papers from this data. So these objects are really, really interesting. And here, for the comparison, we see the frames obtained from down mission and frames from VLT. This is a really great technique to all surface special features are detectable from VLT observations. So this is, you will know more about it in the next weeks. So thank you very much. And
thank you very much. Very exciting. I'll just check that Edyta will speak here on the 30th of November, so in 4 seminars. So questions, please. Here, Milan.
Yeah. Yeah, this is, maybe the theory is not perfect, still not perfect. We don't know how it could exist here. These lines were that this theory is developed by I forgot the name. Englishman. And I think he will improve this the theory concerning these parameters which should be used and maybe the diameter, no, the density is wrongly assumed for this object. Yes. If you want to know more about Sage Code, you have to invite Przemo.
I forgot we should repeat the question because it will not get recorded. So you might. There was a question from Tom.
In the whole solar system. In fact, the mass of the objects are not. It's not large. It's about, I think, as I remember, it's several masses of the Earth. So. We know that the object larger than 1 kilometer should be about 1 million. But about the mass, I don't remember if. I think it's completely different population.
Okay. You? Any more questions here from the audience? I'll check if there are any questions. I don't see any. I have just one. You said these occultations, it's a pretty cool technique. You need a lot of observers. But how long does it last per observer, and how precise you know the timing?
You know, the really good cameras are needed because it depends on the size of the object, but usually it lasts about 4 seconds. So we need a really fast photometry, 0.2 second readout, or maybe stacking of images or something like this. But
and how well you know? Is it within this? So tonight it's going to happen, or you can precisely pin to an hour or to a minute?
We precisely know even by second when it should happen. Yeah. But of course, there are some error bars for the position of the star for first, and the position of the object on the orbit. So usually, if the occultation is very important, one night before the occultation, the correction for astrometry is done for the object, and the correction of the orbit is done. So new orbit is defined for the object.
And how faint are the stars you normally observe?
In fact, it does not. It is not important. The star should be detectable. Yeah, exactly. Because the drop is. I don't remember, but it doesn't matter. In fact, the time is important.
But
only the time.
Need to see the star, right?
We need to see the star. If it disappeared, it means that the occultation started, and if it appears, it is the end. We do not have network of robotic telescope, but it's a network of observers. And some of them, they have remote telescopes. Some are, they travel, in fact, to observe occultations. It is a very big group in Europe and also in the United States of the people who like to observe occultations. Yeah, occultation hunters. Mostly amateurs, yes. And to be in a group, they were well prepared for observations, and they need a special. There are some requirements for the equipment, especially time is important, and the location, yeah, so GPS and time.
Fantastic. Thank you. I don't see any more questions, so let's thank our speaker again. Next week, it will be shown on the screen.